Hi science students, this is the first video on projectile motion. So with projectile motion, we're talking about motion like this one in this video here. In this one, I'm going to roll a tennis ball off a table and it will be projected horizontally off that table. So there it goes. Okay, so I'll just stop that, go back a little bit. So you can see that I'm tracking the motion in LoggerPro and it traces out that parabolic path. So it projected horizontally and at the moment it leaves the table it begins accelerating towards the Earth. Now we examine this motion in terms of two components, and those components are vertical and horizontal motion. So I'm going to show you this video here. So this is a cannonball being fired. Now this cannonball is going to be fired diagonally up into the air. We don't study that type of motion in this course, but the same principles still apply. So at the moment it's fired, its velocity is diagonally in this direction. Now that can be split into components of vertical and horizontal velocity. Okay, I'll just go a little bit. So we see here we've got the vertical velocity, horizontal velocity in the x direction and the vertical velocity in the y direction. Right, now what will happen is that this horizontal velocity is going to remain constant throughout the flight, or this vertical velocity will change. Let's watch. So the green arrow disappears and then reappears again as it accelerates towards Earth. Now if we just back it up a little bit, this is what we do study is motion like this from now on. Right now this projectile is starting out going horizontally. Now as vertical velocity increases, it will start to make the result, this orange arrow, start to come more diagonally downwards as we go along through the flight. So watch this. So vertical velocity increasing, and by the end the ball is going in this diagonal direction, and we can sort of take those arrows top to tail them, those horizontal and vertical arrows, which will result in this velocity. So having a look at the video here, I split this into the different components. So if we look at, actually I've got a different presentation for that one, bear with me. So if we look at the graphs of this, so firstly here I've got the x displacement. So you can see that the tennis ball in the horizontal plane is moving further from the origin. So that is the same. So that gets out to just over 30 centimeters. So that is the same as this distance from here to here. That's about 30 centimeters from the edge of the table to here. That's how far it goes horizontally. And it does that at a constant rate because the horizontal component of the velocity is non-accelerated. So if I look at that horizontal component, see how it stays the same for the horizontal velocity, relatively flat horizontal line. Now in terms of the vertical velocity and the vertical displacement, well, we see here that the vertical displacement increases slowly at first and then more rapidly because the ball's accelerating. In terms of the velocity, that increases in the negative direction. This looks curved. It actually should be a straight line. I'll put a bit of a straight line on that. Just my data collection error, but that should really be going down at a constant rate. But the velocity in the vertical direction becoming increasingly negative because we're saying negative downwards is the negative direction, so getting faster in the downwards direction. Right, so let's do some work on this, and this should help to shed some light on what we're talking about here. So, just a reminder here, this is the type of motion we're going to study where the projectiles are projected horizontally, not at these diagonal type directions. Let's have a look at this one. So here we've got this cannonball and it's being projected horizontally at 1 meter per second. So 1 meter per second in that direction the moment it comes out of the cannon. Now it's actually going to begin accelerating towards Earth, and the cannonball traces this path through the green ball. That's what it actually does. But we're going to examine it in the two components of horizontal and vertical displacement. We're going to look at the blue, the horizontal first. So I'll get a blue pen. Okay, so because we're looking at horizontal, we can see that the gaps between the cannonballs are the same, so it's traveling at constant velocity. So we're going to use that equation we learnt right back at the beginning of the unit, where velocity is equal to displacement over time. Non-accelerated motion. So after 3 seconds, the displacement, well, first we need to rearrange this. This means that displacement is equal to velocity times time. So after 3 seconds, the displacement is equal to velocity, which was 1 meter per second, times 3 seconds. So it's traveling at 1 meter per second for 3 seconds. It's going to go 3 meters. So this will be 3 meters from here to here. What about after 6 seconds? Try it yourself. Might want to pause the video and have a go, then I'll show you the answer. Okay, so it's traveling at 1 meter per second for 6 seconds, so it's going to go 6 meters. So 6 meters all the way to there. So in the horizontal direction, we have non-accelerated motion, constant velocity. Okay, now, what about vertically? Now we can see that vertically, the gaps between the balls are getting bigger each second. Okay, so it's accelerating towards Earth. Now once we start with accelerated motion, what's our magic word? That's right, suvat. So you might want to pause the video at this stage and go ahead and decide what the variables are for the suvat, then I'll discuss them. Okay, so in this case, we're trying to find the vertical displacement, so that's our question mark. The initial velocity. Well, what is the initial velocity in the vertical plane? Well, if we look back at our y velocity here, initially, actually, I'll look at this one here rather. Our y velocity starts up at 0 to begin with, so it's the vertical velocity will be starting at 0. So the initial velocity in the vertical direction is always 0. It's just like it's been dropped. Okay, we're not really interested in the final velocity at this stage. It's accelerating towards Earth at what rate? 9.81 meters per second. And the time, our first one is 3 seconds, and then we're going to go at 6 seconds. So you might want to pause now and see if you can calculate this on your own. Then I'll have a go at it. Okay, so the first one, let's see. We're going to be using the third equation of motion, S equals ut plus a half at squared. So in this case, u is equal to 0. Remember, that makes this thing disappear to 0, that term in the equation. So we're just using S equals a half at squared. So for the first one, at 3 seconds, it's a half times 9.81 times 3 squared. And for the next one, a half times 9.81 times 6 squared. So, oops a daisy, 0.5 times 9.81 times 3 squared is 44.145. And 0.5 times 9.81 times 6 squared is, oh, that's not right, is it? Sorry, try that again. 0.5 times 9.81 times 6 squared gives 176.58. Okay, so those are the two displacements for that one. Okay, so go ahead now and have a go at this one here on your own. It's very similar to what we've just looked at. Then you can look up the solutions to this one on Canvas and check your answers. In the next video, I'll be looking at this question here about the two oranges. So I better not give you too much of a surprise there, but we'll talk more about that one later, and we'll look at some other aspects of projectile motion. Okay, thanks for watching.